Okay, in this video we will explain how to compute the eigenvalues and eigenvectors of a 2 by 2 matrix. Let me start with some definitions. Let me say definition. If we have a 2 by 2 matrix, let's say A, B, C, and D, then we compute the trace. We define the trace of A, denoted like TR of A, just as the sum of these two elements, A plus D. The determinant of A, just denoted like DET of A, is AD minus BC, and the characteristic equation, of that matrix is lambda squared minus the trace of A times lambda plus determinant of A equals 0. This is called the characteristic equation. More than that, if we have this matrix A, B, C, D, and we multiply this matrix by a vector V1, V2, then we get another vector. We get the vector A, V1 plus B, V2, C, V1 plus D, V2. Right? But then we're going to say that a vector V1, V2 is an eigenvector. Then let's say that we say that V1, V2 is an eigenvector of A if A times B1, B2 is equal to some lambda times B1, B2, where this lambda, it could be a complex number or a real number. And another important property for an eigenvector is that we're going to request that this eigenvector is different from 0. Then we're going to assume that this is different from 0, 0. Okay, let's do some examples. Let's think about a matrix. Let's say the matrix 2, 3, 4, 5, right? And let's think about a vector. What vector can I pick? Let's say the vector 1, 2. Then is 1, 2 an eigenvector of this matrix? In order to check that, we do this product. When we multiply, what do we get? We get 2 plus 6 is 8. And here is 4 plus 10, 14. Then the question is this vector a multiple of this? If it were, then since this is 1 and this is 8, this will be 8 times, but 8 times 2 is not 14. Therefore, we can say that this vector, 1, 2, is not an eigenvector of this matrix. Along with the notion of eigenvector, we have the notion of eigenvalue. Let me just say here, we have defined what is an eigenvector. An eigenvector is a vector with the property that when you multiply the matrix by the vector, you get a multiple of the vector. And when that happens, we say that lambda is an eigenvalue. Then we say that lambda is an eigenvalue if there is an eigenvector V equal to B1, B2 such that A times V equal lambda V. Notice that it looks like we first compute the eigenvectors and then the eigenvalues, right? Because the eigenvector, when you have an eigenvector produces an eigenvalue. But when we're going to do computations, we're going to find out that we first compute the eigenvalues and then the eigenvectors. But let's just have an example of an eigenvector and a matrix. If we have the matrix 0, 1, negative 1, 0, we can check that the vector v equal to 1i is an eigenvector of this matrix. Why is that? If we do a times v, this will be 0, 1, negative 1, 0 times 1i. And when we do this product, we get I times negative 1. But we can check that this vector is just I times 1 and 1i. Notice that I times 1 is I, and I times I is negative 1. That means that this vector is an eigenvector of A, and what would be the eigenvalue? The eigenvalue would be I. Then I is an eigenvalue of A, and V is an eigenvector of A. But as I mentioned before, this is not the way that we compute eigenvalues and eigenvectors. We're going to be using this theorem to compute the eigenvalues. We first compute the eigenvalues and then the eigenvectors. Let me write down the theorem that we're going to use. We have this theorem. And it says that lambda is an eigenvalue of A equal A, B, C, D if and only if lambda squared minus the trace of A lambda plus determinant of A is equal to 0. Okay, that means that lambda is an eigenvalue of A if and only if lambda satisfies the characteristic equation for A. Now that we have how to compute eigenvalues, the following theorem will tell us how to compute the eigenvectors. Let's say theorem, and it says that if lambda is an eigenvalue of A, that means if lambda satisfies this equation, then the system of equations let me erase this part. The system of equations A minus lambda times x plus b times y equals 0, and cx plus d minus lambda y equals 0, it has infinitely many solutions. Infinitely many solutions. And then all of them different from 0, 0 are eigenvectors of A associated with lambda. Let's do the previous problem, and we will be using both theorems to compute the eigenvalues and the eigenvectors. Okay, let's have this example. Let's suppose that we have the matrix A equals 0, 1, negative 1, 0. Then, in order to compute the eigenvalues, we compute the characteristic equation, then we compute the trace of A, which is 0, and the determinant of A, which is 0 minus negative 1, it would be 1. Then the characteristic equation is lambda squared plus 1 equals 0. And that means that lambda equal plus or minus I. Then if we want to compute the eigen vectors, then we pick one of them for lambda equal I. Then according to this theorem, it says that this system of equations, 0 minus I, 0 minus lambda times x plus b, 1 times y equals 0. And c, which is negative 1 times x plus 0 minus I times y equals 0. That is the system negative I x plus y and negative x minus iy equals 0. This theorem says that since this lambda is an eigenvalue, since this lambda satisfies the characteristic equation, then this system has infinitely many solutions. And then we can find eigenvectors by solving that system. Something that is going to be important is that if we have a solution, how to pick a solution of this, a non-zero solution. Notice that if we have a solution, an equation that looks like ax plus by equals 0, how do we easily find a solution of this? Let's say that we have 13x minus 237y equals 0. How to pick a non-zero solution easily for this? We can always pick x equal b. We can make x equal b, then we get a times b, and y equal negative a. This will always work. Then for this equation, we can pick x equal negative 237 and y equal negative 13. You can check that this negative 237, negative 13 is a solution of this equation. And that will always work, even if you have something like, let's suppose that you have an equation of the form 2 plus 3i times x minus 17 plus 2i, let's say plus 17 minus 2iy equals 0. How do we pick a solution for this? We can make x equal 17 plus 2i, and we can make y equal the opposite of this, negative 2 minus 3i. That means that the point 17 plus 2i and negative 2 minus 3i is a solution of this equation. That will always work. Then let's go back to the particular problem. The theorem says that this has infinitely many solutions, but then one solution of this will be a solution of that. If we think about this equation, we can pick x equal the coefficient of this, which is 1, and y equal the coefficient of x, negative the coefficient of this, which is negative I, it will be I. That means that 1i satisfies both equations. Easily we can check that it satisfies the first equation, negative I times 1 is negative I plus y equal y plus I equals 0. But it also satisfies the second equation. We have negative 1 minus I times y is I, and this is equal to 0 because I times I is positive 1, and negative 1 plus 1 equals 0. Then we have found an eigenvector that goes with lambda equal I. We can do the same if we want to pick, if we decide to do for lambda equal negative I, we can also find another eigenvector. Another observation is that if we have an eigenvector, any multiple of this is also an eigenvector. Then if you're looking for an eigenvector, a non-zero vector that solves both equations, if this one does, if this one solves the system, then if you can multiply by any number, let's say by 2, then this also works. or you can multiply this by I. If you multiply by I, what do you get? I negative 1. This also works. Then once you have an eigenvalue, when you multiply by any number, that will also be an eigenvector. Sorry, once you have an eigenvector, if you multiply by any number that you pick, you get also an eigenvector. Then eigenvectors are not unique. Let's think about another example. Let's consider the matrix A equal 4, 1, negative 5, negative 2. And let's find the eigenvalues and eigenvectors. Then, to find the eigenvalues, we compute the trace. The trace of A is 2, and the determinant of A is negative 8 plus 5, which is negative 3. That means that the characteristic equation is lambda squared minus the trace, minus 2 times lambda, plus the determinant equals 0. That means that we can factor this by like that, right? Two numbers that multiply this negative 3, and 1. That means that the eigenvalues are lambda equal 3 and lambda equal negative 1. Now let's compute the eigenvectors. Then for lambda equal 3, we have that the system that we need to solve is A, which is 4 minus 3 times x plus plus y equals 0, and here is negative 5x plus d minus lambda times y equals 0. If everything is okay, these two equations are supposed to be the same, and we have here x plus y equals 0 and negative 5x minus 5y equals 0. And as I mentioned before, you can always pick x equal this coefficient, which is 1, and y equal the opposite of this coefficient, which is negative 1. Notice that if we use this equation, we're going to get, I can pick x equal negative 5 and y equal the opposite of negative 5, which is 5. And these two are essentially the same. One is a multiple of the other. Then both will work as a particular eigenvector for this eigenvalue. We can actually check that this is an eigenvector. Remember the definition of eigenvector? An eigenvector is a vector that has the property that when you multiply this matrix by this vector, you get a multiple. Let's check that. Usually you don't have to check that, but just to check, let's just do it this time. 4, 1, negative 5, negative 2 times 1, negative 1. What is the product of this vector by this matrix? We have 4 minus 1 is 3, and negative 5 plus 2 is negative 3. Is this a multiple of that? Yes, it is. And what is the multiple? You can write it as 3 times 1, negative 1. Then we see that this is an eigenvector, because when you multiply the matrix by that vector, you get a multiple of the vector, and that multiple is an eigenvalue. And as I mentioned before, you first compute the eigenvalues and then you compute the eigenvectors. Let's compute the eigenvector that goes with the other eigenvalue. Then for lambda equal negative 1, what is the system that we need to solve in order to find the eigenvectors? We have 4 minus negative 1, it will be 4 plus 1 times x plus y equals 0, and negative 5x plus negative 2 minus lambda times y equals 0. If everything is okay, these two equations are the same. It will be 5x plus y equals 0, and here negative 5x minus y equals 0. They are essentially the same, and a solution for this would be x equal 1 and y equal negative 5. Then an eigenvector for this eigenvalue is 1, negative 5. Remember that there are infinitely many. Any multiple of this will work, and an eigenvector for this will be 1, negative 1. And any multiple of this would be also an eigenvector.